Hi friends, welcome back to our YouTube channel. Today we have to discuss about BCD Synchronous Up Counter or Mod 10 Synchronous Up Counter in Digital Electronics course, Digital Logic Design course and Switching Theory and Logic Design course. It is one of the most important concepts in these courses. First of all, how to design Mod 10 Synchronous Up Counter or BCD Synchronous Up Counter. To design this counter, we have to use 6 steps. The first step is determine how many number of flip-flops are required to design BCD Synchronous Up Counter or Mod 10 Synchronous Up Counter and decide which flip-flop we have to use. This is the first step. We already know that Mod N counter contains n number of states. In the same way, Mod 10 counter contains how many number of states? So that is 10 states. Okay, so therefore number of states capital N, that is equal to 10 states. So 10 states are nothing but 0 to 9 states. Now, maximum count value. Maximum count value is equal to n minus 1, whereas n is nothing but number of states, that is a 10. So 10 minus 1, that is equal to 9. Total 10 states are present in BCD Synchronous Up Counter or Mod 10 Synchronous Up Counter, starting with 0 and ending with 9 state, because maximum count value is equal to 9. Okay, next, how many number of flip-flops are required to design this BCD Synchronous Up Counter or Mod 10 Synchronous Up Counter can be calculated by using this formula. Capital N less than or equal to 2 power small n, where capital N is nothing but number of states present in BCD or BCD Synchronous Up Counter or Mod 10 Synchronous Up Counter. That value is 10 less than or equal to 2 power n. Small n is nothing but number of flip-flops are required to design Mod 10 Synchronous Up Counter or BCD Synchronous Up Counter. Now substitute n value. If n value is equal to 3, then 10 less than or equal to 2 power 3. So that implies 10 less than or equal to 8. So this is false. Next, substitute n is equal to 4. If n is equal to 4, then 10 less than or equal to 2 power 4. That implies 10 less than or equal to 16. So that is true. So for which value of n this formula is satisfied? So small n is equal to 4. So therefore number of flip-flops can be denoted by small n, that is equal to 4. Now up to now we know that how many number of flip-flops are required to design BCD Synchronous Up Counter or mod 10 Synchronous Up Counter, that is 4. How many number of states that are present in BCD Synchronous Up Counter or mod 10 Synchronous Up Counter, that is 10 states starting with the 0 state and ending with the 9th state. Next, which flip-flop we have to use? Here we have to use either JK flip-flop or T flip-flop we have to use. So in this problem I am using JK flip-flop. Here we have to use JK flip-flop to design BCD Synchronous Up Counter or mod 10 Synchronous Up Counter. This is the first step. Now we can go for second step. Write the excitation table of decided flip-flop. Here the decided flip-flop is JK flip-flop. Now we have to write the excitation table of JK flip-flop. In the excitation table, the inputs are present state and next state. So present state is nothing but Qn and the next state is nothing but Qn plus 1. Next, the excitation inputs are J and K. So these are called as excitation inputs. Now, here with the two inputs, how many number of possible combinations we are getting? 4 possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. 4 possible combinations we are getting. For each and every possible combination, we have to write the excitation inputs values. First combination, Qn value is 0, Qn plus 1 value is 0, J value 0 and K value is don't care. Next, Qn value is 0, Qn plus 1 value is 1. The excitation inputs are 1 and don't care. Qn value is 1, Qn plus 1 value is 0. The excitation inputs are don't care, 1. Qn value is 1, Qn plus 1 value is 1. The excitation inputs are J value is don't care and K value is 0. How to write the excitation table? Please refer the video JK flip-flop using NAND gate and JK flip-flop using NOR gate. In that video, how to write the characteristic table. From the characteristic table, how to write the excitation table. So for better understanding, please refer that video. Next, step 3 is draw the state diagram of BCD Synchronous Up Counter or mod 10 Synchronous Up Counter. So total 10 states are there. total 10 states are there. So that are state number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 to 9. Total 10 states are there. Starting state starts with the 0 and ending state starts with the 9. Maximum count value. Okay. Next. How many number of bits we have to use to represent each and every state? So, in BCD stands for binary coded decimal. In BCD, the valid digits are 0 to 9. Total 10 digits are there. To represent each and every digit, we have to use 4-bit binary. Okay, so each and every digit, to represent that each and every digit, we have to use 4 bits. Okay, so first BCD digit, that is a 0, that is a 0 state, we have to use 4 bits to represent 0 state. Next, to represent one state, we have to use 4 bits. To represent second state, we have to use 4 bits, 4-bit binary. Next, to represent state 3, we have to use 4 bits. To represent state 4, we have to use 4 bits. To represent 5 state, we have to use 4-bit binary. To represent 6th state, we have to use 4-bit binary. To represent 7th state, we have to use 4 bits. To represent 8th state, we have to use 4 bit. To represent 9th state, we have to use 4 bit. Okay, so here the counter starting with 0 and goes to state 1, goes to state 2, goes to state 3, goes to state 4, goes to state 5, goes to state 6, goes to state 7, goes to state 8, goes to state 9, and again it goes to state 0 after reaching the maximum count value. Okay, next one. Each and every state 4 bits are there. In that 4 bits, so here this bit is called as Q3 bit. Sorry, this bit can be treated as Q1 and this bit can be treated as Q3. You have to use your own way. This bit can be treated as Q3 and this bit can be treated as Q1. No problem at all. Okay, I am taking MSB bit can be treated as Q1 and LSB bit can be taken as Q3. Okay, next, this is the state diagram of mod 10 synchronous up counter or BCD synchronous up counter. Next, we can go for step 4. In that step 4, we have to draw the circuit excitation table for BCD synchronous up counter or mod 10 synchronous up counter. How to write the circuit excitation table using step 3 and step 2. Now here there are 6 columns are there in the circuit excitation table. The first column contains the 4 bits Q1, Q2, Q3, Q4. So that can be called as present state bits. Second column contains Q1 plus, Q2 plus, Q3 plus, Q4 plus, that are called next state bits. For Q1 state, the next state is Q1 plus. For Q2 state, the next state is Q2 plus. For Q3 state, the next state is Q3 plus. For Q4 state, the next state is Q4 plus. Q1, Q2, Q3, Q4 belongs to present state, whereas Q1 plus Q2 plus Q3 plus Q4 plus represents next state. Now, J1, K1, J2, K2, J3, K3, J4, K4 are called as excitation inputs. Okay, for calculating J1, K1, we have to use Q1, Q1 plus as inputs. For calculating J2, K2, we have to use Q2, Q2 plus as inputs. For calculating J3, K3 column, we have to use Q3, Q3 plus as inputs. For calculating J4, K4, we have to use Q4, Q4 plus as inputs. Now, first, the present state, the first state is 4 zeros. So, starting with, this state, 0, 0, 0, 0. Whenever the present state is 0, 0, 0, 0, what is the next state? The next state is 0, 0, 0, 1. Now, this next state can be taken as present state 0, 0, 0, 1. What is the next state for 0, 0, 0, 1? That is 0, 0, 1, 0. Now 0, 0, 1, 0 can be taken as present state. What is the next state for 0, 0, 1, 0? That is 0, 0, 1, 1, 1. Now 0, 0, 1, 1 can be taken as present state. What is the next state for 0, 0, 1, 1? That is 0, 1, 0, 0. Now 0, 1, 0, 0 can be taken as present state. What is the next state? 0, 1, 0, 1. Now 0, 1, 0, 1 can be taken as present state. What is the next state? 0, 1, 1, 0. Now 0, 1, 1, 0 can be taken as present state. What is the next state? 0, 1, 1. Now 0, 1, 1 can be taken as present state. What is the next state? 1, 0, 0, 0. Now 1, 0, 0 can be taken as present state. What is the next state? 1, 0, 0, 1. Now 1, 0, 0, 1 can be taken as present state. What is the next state? 0, 0, 0, 0. Again, it goes to the starting state. Okay. Here we have to consider one important point. Okay. With 4 bits, how many number of possible combinations we are getting? So n is nothing but number of bits in the present state, 4 bits. How many number of possible combinations we are getting? So 2 power 4, 16 possible combinations we are getting. Among that 16 possible combinations, 0 to 9 are valid. 0 to 9 combinations are valid, and 10 to 15 are invalid. This point is used in next step, step 5. Okay, so here we have to use only 0 to 9 are valid state and 10 to 15 are invalid state. Here 1, 0, 1, 0. So here 1, 0, 1, 0, 2, 1, 1, 1 are invalid states. Invalid states. These invalid states cannot be represented in this circuit excitation table. Please keep this point in your mind in step 5. Okay. Now, how to fill this circuit excitation table? For G1, K1, we have to use Q1 and Q1 plus as inputs. Now, see this one. Q1 value is 0, Q1 plus value is 0. What is the circuit excitation inputs? 0, don't care. Here we have to write 0, don't care. Q1 value 0, Q1 plus value is 0, J1, K1 values are 0, don't care. Q1 value 0, Q1 plus value is 0, so J1, K1 values are 0, don't care, according to this step. Q1 value is 0, Q1 plus value is 0, so J1, K1 value is 0, don't care. Q1 value is 0, Q1 plus value is 0, 0, don't care. Q1 value is 0, Q1 plus value is 0, 0, don't care. Q1 value 0, Q1 plus value is 0, J1, K1 value 0, don't care. Q1 value is 0, Q1 plus value is 1, 0, 1. What is the excitation inputs? 1, don't care. Q1 value is 1, Q1 plus value is 1, 1, 1. So don't care, 0. Next, Q1 value is 1 and Q1 plus value is 0, 1, 0. So don't care, 1. Next one. For filling out J2, K2 column, we have to consider Q2, Q2 plus as inputs. First, Q2 value 0, Q2 plus value is 0, 0, 0. Excitation inputs are 0, don't care. Q2 value 0, Q2 plus value is 0, 0, don't care. Q2 value 0, Q2 plus value is 0, 0, don't care. Q2 value 0, Q2 plus value is 1, 0, 1, 1, don't care. Next, Q2 value is 1, Q2 plus value is 1, 1, 1, don't care, 0. Next, Q2 value is 1, Q2 plus value is 1, so don't care, 0. Q2 value is 1, Q2 plus value is 1, don't care, 0. Next, Q2 value is 1, Q2 plus value is 0, 1, 0, don't care, 1. Q2 value is 0, Q2 plus value is 0, 0, don't care. Q2 value is 0, Q2 plus value is 0, 0, don't care. Next, for filling out J3, K3 column, we have to consider Q3, Q3 plus as inputs. 0, Q3 value is 0, Q3 plus value is 0, 0, don't care. Q3 value is 0, Q3 plus value is 1, 0, 1, 1, don't care. Q3 value is 1, Q3 plus value is 1, 1, 1, don't care, 0. Q3 value is 1, Q3 plus value is 0, 1, 0, so don't care, 1. Q3 value is 0, Q3 plus value is 0, 0, don't care. Q3 value is 0, Q3 plus value is 1, so 1, don't care. Next, Q3 value is 1, Q3 plus value is 1, 1, 1, don't care, 0. Q3 value is 1, Q3 plus value is 0, 1, 0, don't care, 1. Q3 value 0, Q3 plus value is 0, 0, don't care. Q3 value is 0, Q3 plus value is 0, 0, don't care. In this way, we have to fill J3, K3 column. Next column is for filling out J4, K4 column, we have to use Q4 and Q4 plus as inputs. Q4 value 0, Q4 plus value is 1, 0, 1. Excitation inputs are 1, don't care. Q4 value is 1, Q4 plus value is 0, 1, 0, don't care, 1. Q4 value 0, Q4 plus value is 1, 0, 1, that is 1, don't care. Q4 value is 1, Q4 plus value is 0, 1, 0, don't care, 1. Q4 value is 0, Q4 plus value is 1, 0, 1, 1, don't care. Q4 value is 1, Q4 plus value is 0, 1, 0, don't care, 1. Q4 value is 0, Q4 plus value is 1, 0, 1, 1, don't care. Q4 value is 1, Q4 plus value is 0, 1, 0, don't care, 1. Q4 value is 0, Q4 plus value is 1, 0, 1, 1, don't care. Q4 value is 1, Q4 value is 0, 1, 0, don't care, 1. In this way, we have to fill circuit excitation table. After that, in step 5, we have to find out for each and every excitation input J1, K1, J2, K2, J3, K3, J4, K4. We have to draw the circuit. We have to find out the simplified Boolean expression using 4 variable Karnaugh map. Here we have to use 4 bits, so that we have to write 4 variable Karnaugh map to find out the simplified Boolean expression using K-map. In step 5, we have to find out the simplified Boolean expression using J1, K1, J2, K2, J3, K3, J4, K4 using 4 variable Karnaugh map. So this is the structure of 4 variable Karnaugh map for J1, K1, J2, K2, J3, K3, J4, K4. For saving of time, I am explaining each and every one. Okay. For J1 column, for each and every Karnaugh map, the invalid states are 10 to 15. So this is 10, 11, 12, 13, 14, 15. 10, 11, 10, 12, 13, 14, 15. So each and every Karnaugh map 10 to 15 are filled with don't cares because they are invalid states. Now observe J1 Karnaugh map. So horizontal side I am taking Q1, Q2. Vertical side I am taking Q3, Q4 as inputs. Now observe J1 column. In that column only don't cares and ones we have to consider. Here 1 is there. The corresponding input combination is 0, 1, 1. 0, 1, 1, 1. We are placing 1. Next one. Here don't care is there. The corresponding input combination is 1, 0, 0, 0. 1, 0, 0, 0. We are placing don't care. Here don't care is there. The corresponding input combination is 1, 0, 0, 1. 1, 0, 0, 1. We are placing don't care. So here 8 don't cares are there. They cannot be formed as oct. Okay. Only single pair we are getting. This one and this don't care can be formed as a pair. Okay. For this pair, horizontal side, so here 0, 1, 1, 1 is there. The first digit belongs to Q1, 0, 1. Both are different. We have to ignore them. Second digit 1, 1. Same digits are there. We have to consider this one belongs to Q2. So here I am writing Q2. In the column side 1, 1 is there. This one belongs to Q3. This one belongs to Q4. So we have to write Q3, Q4 for 1, 1. So answer is Q2, Q3, Q4 is the simplified expression for J1. Next, for K1, observe the K1 column and identifying ones and don't cares. So here, this don't care starts with 0, 0, 0, 2 up to 7. Okay, 0, 1, 1, 1. So 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. So 8 cells are filled with don't cares. Okay. Next one is here only single one is there. So the corresponding input combination is 1, 0, 0, 1. Here 1, 0, here 0, 1. We are placing 1. Okay. So this one and this 7 don't cares can be formed as oct. Okay. Now what is the expression we are getting? For this oct, horizontal side, the first digit belongs to Q1, 0, 0, 1, 1. It contains a combination of zeros and ones. We have to ignore them. Second digit belongs to Q2. It contains a combination of zeros and ones. We have to ignore them. Column side, here 0, 1, 1, 1 is there. The first digit belongs to Q3. it contains 0 and 1. Both are different. Simply we have to ignore them. Second digit belongs to Q4. It contains 1, 1. So same digits are there. We have to consider that Q4 value is 1 is nothing but Q4. So the simplified expression for K1 is Q4. Next. For J2, observe the J2 column and identify ones and don't cares. Here 1 is there, the corresponding input combination is 0, 0, 1, 1. Next one, don't care is there, the corresponding input combination is 0, 1, 0, 0. Next here don't care is there, the corresponding input combination is 0, 1, 0, 1. Here don't care is there, the corresponding input combination is 0, 1, 1, 0. Here don't care is that the corresponding input combination is 0, 1, 1, 1. And here 10, 11, 12, 13, 14, 15 are invalid states. They can be represented with don't care. So now this one, these three don't cares can be formed as quad. Okay. For this quad, horizontal side contains 0, 0, 0, 1, 1, 1, 1, 0. So first digit contains a combination of zeros and ones. Simply we have to ignore Q1. The second digit contains a combination of zeros and ones. So Q2 is ignored because it contains a combination of zeros and ones. Column side only 1, 1 is there. The first digit belongs to Q3, second digit belongs to Q4. Q3 value is 1, Q4 value is 1. Therefore, the simplified expression is Q3, Q4 for J2. Next, for K2, identify the K2 column and observe the ones and don't cares. So here, don't care starts with 0, 0, 0, 0 and end with 0, 0, 1, 1. So 0, 0, 0, 2, 0, 0, 1, 1. The first row is filled with don't cares. Next one is, here 1 is there, the corresponding input combination 0, 1, 1, 0, 1, 1, 1, we are placing 1. Next one is, here don't care is there, 1, 0, 0, 1, 0, 0, 0, we are placing don't care. Here don't care is there, 1, 0, 0, 1, 1, 0, 0, 1, we are placing don't cares. So 1, this don't care, this don't care, this don't care can be formed as quad. It is similar to this one, so that the expression for K2 is Q3, Q4. Okay, next. For J3, so identifying the J3 column and observe only ones and don't cares. Here 1 is there, the corresponding input combination is 0, 0, 0, 1. Next here don't care is there, the corresponding input combination is 0, 0, 1, 0. Here don't care is there, the corresponding input combination is 0, 0, 1, 1. Next here 1 is there, the corresponding input combination is 0, 1, 0, 1. Next here don't care is there, the corresponding input combination is 0, 1, 1, 0. Here don't care is there, the corresponding input combination is 0, 1, 1, 1. And 10, 11, 12, 13, 14, 15 are invalid state. They can be represented with don't cares. So now here don't care is there. They can be formed with ought. But here it is a vacant place, so this 1, 1 don't care can be formed with the quad. For this quad, horizontal side 0, 0, 0, 1 is there. The first digit is 0. It contains the same digit, so that we have to consider Q1 value is 0 is nothing but Q1 bar. And second digit 0, 1, both are different, so that we have to ignore Q2. For the column side 0, 1, 1, 1 is there. The first digit is 0, 1, both are different, so that we have to ignore the Q3. The second digit contains 1, 1, both are same. We have to consider Q4. Q4 value 1 is nothing but Q4. Here we have to write Q1, here we have to write Q4. So Q1 bar Q4 is the simplified expression for J3. Okay, next one. For K3, observe the K3 column and identifying don't cares and ones. Here don't care is that the corresponding input combination is 0, 0, 0, 0. Here don't care is that the corresponding input combination is 0, 0, 0, 1. Next one, Here 1 is there, the corresponding input combination is 0 0 1 1. Next one, here don't care is there, 4 and 5 are don't cares. So 4 5 are don't cares. Next one, here 1 is there, 0 triple 1. So 0 1 1 1 we are placing 1. Next one, 8 and 9 are don't cares. So 8 and 9 are don't cares. So now, sorry, 8 and 9 are don't cares. So here they can be formed as oct. Okay, so here they can be formed as oct. So for this oct, horizontal side contains a combination of zeros and ones. So therefore Q1 column and Q2 column are discarded, ignored, and vertical side first digit 0 1, it belongs to Q3, both are different, so that we have to ignore them. The second digit contains 1 1, we have to consider Q4, therefore Q4 value is 1, therefore Q4 is the simplified Boolean expression for K3. Next one, for J4, observe this one, all are filled with ones and don't cares. For K4 also, all are filled with ones and don't cares. So these 8 cells can be found with oct, these 8 cells can be found with oct. So then here we are getting as Q3 bar, here we are getting as Q3 bar plus Q3, it is 1, therefore J4 value is 1. In the same way, K4 also, this is Q3 bar and this is Q3. Q3 plus Q3 bar is equal to 1. Therefore, K4 is equal to 1. If any Carnot map is filled with ones and don't cares, its value is 1. So these are the simplified expressions for J1, K1, J2, K2, J3, K3, J4, K4. Now we can go for draw the logic diagram. In step 6, we have to draw the final logic diagram by using the simplified Boolean expressions that we are getting from step 5. Here to design BCD Synchronous Up Counter or mod 10 Synchronous Up Counter, we have to use 4 JK flip-flops. This is the first JK flip-flop, second JK flip-flop, third JK flip-flop, fourth JK flip-flop. For the first JK flip-flop, inputs are J1, K1 and outputs are Q1, Q1 bar. For second JK flip-flop, J2, K2 are the inputs, Q2, Q2 bar are the outputs. For the third JK flip-flop, J3, K3 are the inputs, Q3 and Q3 bar are the outputs. For fourth JK flip-flop, J4, K4 and are the inputs, Q4, Q4 bar are the outputs. The output of the first flip-flop is Q1. It can be treated as MSB. For output of second flip-flop, that is Q2. For the output of third flip-flop, Q3. For the output of fourth flip-flop, that is Q4. It can be considered as LSB. All the 4 JK flip-flops are synchronized by using the same clock pulse. Therefore, the same clock pulse is applied for 4 flip-flops at the same time. It is a negative edge triggered clock pulse. Okay. Now, what are the inputs we are applying? J1, K1, J2, K2, J3, K3, J4, K4. That are here. Okay. Now, first one, J4 value 1, K4 value is 1. So, here J4 and K4. I am writing this one. So J4, K4. So their values are ones. 1 can be passed to J4 and the same 1 can be passed as K4. Next one is K3 value is Q4. Okay. K3 value is Q4. So here Q4 value is there. This is Q4. So this is Q4 that can be passed to K3. So K3 value is Q4. Next one, J3 value is Q1 bar and Q4. So here this is Q1 bar is there. So I am taking this Q1 bar. So this is Q1 bar. And this is Q4. Pass it to two input and gate. So this is Q4 and this is Q1 bar. Whatever the output we are getting, that output can be passed to J3. So this is Q1 bar, this is Q4 and this is Q1 bar. These two inputs can be passed to two input and gate. Whatever the output we are getting, that output can be passed to J3 and K3 value is Q4. So here I am writing Q4. Okay, next one. Next one is J2 value and K2 value is Q3, Q4. Q3, Q4. So here Q4 value is there. I am taking Q4 and this is Q3 value is there. So this is Q3 and this is Q4. So these can be passed to two input and gate. Two input and gate. Whatever the output we are getting, that output can be passed to K2 and J2. Okay, so here the output is Q3, Q4, Q3, Q4. So this can be passed to J2 and this can be passed to K2. Okay, next one. Q1 value is equal to K1 value is equal to Q4. Okay, so here Q4 value I am taking here. Q4 that can be passed to K1. So K1 is equal to Q4. Here I am writing Q4. Next, J1 is equal to Q2, Q3, Q4. So this can be extended. This is Q4. Next one, Q2, Q3. I am taking Q3. Next, I am taking Q2. Q2. These three can be passed to three input and gate. So whatever the output we are getting, that is Q2, Q3, Q4, that can be passed to J1. So J1 value is equal to Q2, Q3, Q4. Okay, so this is the simplified logic diagram of BCD Synchronous Up Counter over Mod 10 Synchronous Up Counter. I hope all of you understanding this video. If you really understanding this video, please click on the like button and share this video to your friends and classmates. I am clearly explaining each and every step so that it can take approximately 40 minutes. So after listening this video, if you like this video, share this video to your friends and classmates, and please subscribe my YouTube channel Divvela Srinivasarao. After subscribing my YouTube channel, click on the bell icon to get the future updates in my YouTube channel. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. And for better understanding of entire digital electronics course, go to this channel and go to the playlist called DLD, ORR, STLD, ORR Digital Electronics. It contains approximately above 340 videos for better understanding of the entire course. Thank you one and all for watching this video.